going to talk about discrete stochastic processes, and without spending time on first trying to define stochastic processes and on that in discrete stochastic processes in abstraction, I would prefer to give you examples, and then we will try to come to a conclusion and hopefully be able to define, and in fact you would have by that time formed your own definition of stochastic process. Of course, here we are going to first talk about discrete stochastic processes. Now, let us just look at one example. A watch selling shop keeps a particular brand of ladies watch, right, and the let di denote the demand for this brand in the ith week. So, let us just say that our planning horizon is 3 weeks, and so D1 will be the demand for this particular brand of watches in the first week, D2 in the second week, and D3 will be in the third week, right. And these are DIs are random variables, because the demands are not a certain commodity, because otherwise the shopkeeper's job will be very easy. So, here DIs are random variables, and they are identically independently distributed random variables. So, this one simplification has been added here. So, the DIs are not known, they are not certain events, but they have same distribution and independent. So, that means the demand in the first week is independent of the demand in the second week and independent of the demand in the third week. Okay. Let Ni denote the number of watches on hand at the end of the ith week. So, let us say by Saturday evening the man takes stock of his things that he has on hand, and so Ni will be the same particular brand of ladies watch. He has Ni of them. So, that means N1 at the end of the first week, N2 at the end of second week, and N3 at the end of third week. Now, orders placed for watches on Sunday evening are delivered before the shop opens on Monday morning. So, this could be Sunday evening or Saturday evening, whatever it is. So, before the new week begins, so on Monday morning before the shop opens, the watches are delivered, whatever the ordering policy. Okay. Now, suppose the ordering policy followed by the shop owner is as follows: if no watches in stock, order 4 watches. That means, by Saturday evening, if he realizes that he does not have any watch of this particular brand, then he will order for 4 watches, and they will be delivered by Monday morning. Right. So, that means if Ni is 0, order 4 watches. If Ni is 1, that means if he has 1 watch at the end of the week in stock, then he will order for 2 watches. Okay. And finally, if he has 2 or more watches left over by the end of the week, then he will not order any. So, do not order. So, this is his policy, right. And of course, sales are lost when the demand exceeds the number of watches in stock. So, if there is more demand and you do not have that many watches, then you lose those those sales, right. So, fine. So, now let us look at what would be the position in the following week. So, Ni plus 1 will be let us say, so this will Ni plus 1 will denote the number of watches on hand at the end of the I plus 1th week. And how will you compute Ni plus 1 given Ni? So, this will be, you see, if Ni is 0, that means at the, so this is your ith week and this is your I plus 1th week, right. So, therefore, at this point you had Ni watches. Now, if Ni is 0, then you ordered 4 and they were delivered by the time your I plus 1th week started. So, that means then you will have at the beginning, at this point you will have Ni plus 4 watches, and then there is demand Di plus 1. So, that means you would meet the demand, and then depending on whether Di plus 1 is, so since Ni is 0, you will actually have 4 watches on hand, and that is why I have written 4 here. So, actually your this thing will be 4 minus Di plus 1, and if your demand is more than this, then of course you will say the max of this, right, because you can't have negative number of watches, So, either you have 4 minus di plus 1 if di plus 1 is less than 4, or you have no watches left at the end of the next week. So, at this point if you are able to meet the demand di plus 1, then whatever the difference, that will be the watches on hand at this point, otherwise it will be 0 if di plus 1 is more than 4, right. Okay. So, similarly if ni is 2, what were the policies? No, ni is 1, sorry, this is ni is 1. So, if ni is 1, then he orders 2 watches. So, this will be ni plus 2 minus again whatever the demand, and if this number is positive, then that will be taken as the number of watches on hand at the end of the I plus 1th week, otherwise it will be 0. So, ni of course you can write 1 here. So, this is actually max of 3 minus di plus 1 comma 0. So, whichever number is positive, that number you will take. So, when ni is 1, and similarly if ni is greater than or equal to 2, then you are not ordering any watches. 2 or more you do not order. So, your watches on hand at the beginning of the I plus 1th week is ni minus di plus 1 will be what you are left with at the end of the I plus 1th week, and so it will be again max of these 2. So, this is how you can. So, you see the situation at the end of the I plus 1th week is dependent on your situation at the end of the ith week and the demand. So, here are 2 random phenomena on which your state of the system, if you can want to call it, that means the state occupied by the system at the I plus 1th week is given to you by ni plus 1, right, and here this is the current state. So, therefore, you can say that here your ni plus 1s are dependent on just ni and di plus 1. So, the current demand and the state in which you were at the beginning of the I plus 1th week, right. So, this is sort of trying to show you the dependence, because the variables ni plus 1 which we are trying to tell us the state of the system at the end of every week. So, this phenomena is dependent on the 2 random phenomena ni and di plus 1. So, this is one example, and then we will. Now I can sort of give you a definition here saying that ni's indexed by the number of the week form a discrete stochastic process. So, then when you take these n1, n2, n3, so these are 3 random variables and they form a. So, see, the thing is that you are giving them an index which is discrete. So, n1, n2, n3, and the unit of time can be anything. Here it is a week, it could be a month, it could be an hour or whatever it is. So, and therefore, the discrete word. So, this is a random phenomena which is being sort of indexed by discrete time period, and therefore, we will call this a discrete stochastic process. Another example, and therefore, you may. So, of course, this and now okay, the next question to be asked is why study this. So, for example, I have just tried to state 1 or 2 questions that the shop owner may want to have answered, but of course, there can be many other questions that you can also raise. So, for example, the shop owner is interested in knowing the following: long term loss of sales due to his reordering policy. You see, because if he can by some mechanism find out what is the sort of estimate, it may not be an exact number, but he can estimate the number of sales that are lost. When this number is negative, that means he is losing out on sales whenever this number is negative. So, if there is a mechanism by which he can find out what is his long term sales loss of sales due to his reordering policy, because he wants to know whether he really has a good reordering policy or not. Okay. Then and also he may also want to know the effect of changes he makes in his reordering policies. in a reordering policy, right. He may also want to change some of the orders there, and then he would want to know, okay, would that make the situation better, for example, would it reduce his long term because long term word I am using here because it takes a while for any system to settle down. So, we will most of the time when we talk of any stochastic process, we want to analyze it, we would be talking about its long term behavior. So, whatever the disturbances and perturbations, they all settle down after a while, and then we want to look at the system, because otherwise it is very difficult to model any such process. When there are initially a lot of turbulations or lot of perturbations, you cannot really analyze, or you cannot model such a situation. So, therefore, it is a long term loss of sales due to his reordering policies, and then he may want to know if he makes any changes, how will that affect his revenues. Essentially, he is finally interested in the revenues that he gets. Okay. Now, let us look at another example, which is probably a simpler one. So, there is an automobile manufacturing company and has the policy of assigning its white collar employees. So, white collar employees means who work in their office of the sales and so on, to the 3 sections it has. So, the 3 sections it has are production, HR, handling human resources, and sales. So, these are the 3, and then see, we will now look at this example, and again give you another feeling about the stochastic processes. So, the 3 sections are production, human resource, and sales. So, these are 3 sections in the automobile manufacturing company, where he wants to assign the white collar employees, and then I mean by he I mean the owner of that automobile manufacturing company, and there is no set pattern for reassignments, at least the employees do not know. So, there must be something in the mind of the owners how they would reassign. Since there is no set pattern known for the reassignments, one does not know in which section he or she will be assigned next. So, after you have been in one section for a while, certainly you know that you will be transferred, but then you do not know to which one you will be transferred, right. So, the next assignment may depend on the current assignment. It is possible that wherever you are right now, it may have a bearing on where you will be next. So, these are the kinds of. So, then if we let xi denote the section assigned during ith 6-month period. So, that means now you look at one employee's profile. Suppose just take one employee, look at his profile in the sense that you want to keep on measuring. So, your time period is a 6-month time period. That means when you get assigned to a section, it is for a 6-month period, and then after at the end of the 6-month period, there will be another assignment to sections, and you may either stay in the same section or you may get transferred to another one. So, anyway, so let xi denote the section assigned during the ith 6-month period. Okay. And then, so the whole process can be, that means the whole process of the sections being assigned to a particular employee can be described by the sequence x1, x2, so on. So, as long as you are planning horizon, you will have, so x1 will tell you that in the first 6 months the particular employee is in this section, whatever the value of x1, then x2 will tell you the section he is in the second 6-month period, and so on, right. And of course, xi can take the possible values. So, let us number the 3 sections. So, the first section is production, second section is HR, human resource, and the third is sales. So, xi can take 3 possible values, whichever the 3 sections, and so this will describe to you, if you like, you take it up to x10. So, that means for over the 5 years, the sequence x1, x2, x3 up to x10 will tell you the sections to which the particular employee has been assigned, right. So, is a discrete, so this assignment of sections to an employee is a discrete stochastic process, and it is indexed by the periods 1, 2, 3 and so on, right. So, now you get the meaning that, so it is something like the process is evolving over time, and there is uncertainty about the what the state will, I mean where the system would be after each time period. One time period is over, then where will it be next. So, therefore, there is some sort of uncertainty about the whole process, and so this is why we are calling it a stochastic process. Now, for this particular company, an employee may ask the following questions. If an employee is working in sales, what is the probability that after 2 assignments he will be working in sales again? Okay. This particular employee may want to want an answer to this question. Or for example, if the employee is currently in production, how many months must pass on the average before he enters HR, human resource. So, as I said again, just as for the first example, I am stating some questions, you can also add some more. Then the third one, for example, is if the employee has been with the company for 4 years, how many times on the average he would have been assigned to HR, to human resource. Then what percentage of an employee's assignments will be in sales. So, these are the questions and many more. Now, why would these questions be important? Because a prospective employee who is going to join the company can ask questions like this, so that he can judge about his prospects in the company. Basically, he would like to know whether he will professionally be satisfied with the company or not. If it turns out that he comes to know that you will most of the time be with sales, then of course he may not be wanting to stay with the company, because he may not be interested in sales, and so on. So, I am just giving an example, but there can be many such questions that can be asked. So, the ni's of the first example and xi's of the second example are not independent random variables, that you can see, right. In the first example, the ni's were the number of particular brand of watches that were left at the end of the week, that were in stock, and so we saw that this was dependent on what your demand is in the following week, and depended on your ordering policies. So, you can't say that N1, N2, N3 and so on, they are independent random variables, that you can see that there is some relationship, right. And similarly for the xi's, it is possible, see, the whatever the way the organizers or the owners of the company decide to reassign the sections, certainly where you were and how long you have been in a particular section will have a bearing on where you will be next. So, you can feel that these random variables are not independent, right, and therefore, any kind of computations about these random variables will not be an easy thing, right. So, now we will attempt to define this a stochastic process, right, after these two examples. So, any random process for which time can be measured discretely can be represented as a sequence of random variables. So, I should add the word here, and can be represented as a sequence of random variables, then this is I will call it a random process, or I will call it a stochastic process, is called a stochastic process. Right. Or very simply, you can simply say it is a sequence of random variables indexed by time. So, a stochastic process, and definitely you can see that it is evolving over time, and then you want to now look at its behavior. And so, of course, now you see that if you want to answer any of these questions that I have posed, and even in the earlier one, then you see you may want to know, you would need to know the joint density function of, for example, if your planning horizon is 5 years, then you may want to know you would need to know the joint distribution of x1, x2 up to x10, since they are not independent, and therefore, you cannot say that the joint density function of x1 to x10 will be product of individual density functions. So, you will have to need to find out, and of course, if your planning horizon is much bigger, then you can just give raise you can throw up your hands and say that no, I can't compute a joint density function of so many random variables, right. So, therefore, we need to really look at the methods by which we can sort of simplify analyzing such a process, or under what conditions can we try to answer questions like this when we are looking at a stochastic process. So, for the automobile company, just look at we can diagrammatically describe the profile of an employee. And so, you see here the horizontal axis is giving you the time period. So, this is the beginning of the planning horizon. So, 0 period, that means the start of the process. Then this denotes the first 6-month period, this is the second 6-month period, third 6-month period, and so on. So, this is what it is. And then here you have the 3 sections to which the person can be assigned. So, for example, what it is saying is that here in the first 6 months period he was with HR, right, the second section, and then in the next 6-month period he got assigned to production, which is your first section, right. I think this is production, this is HR, and this is sales. So, then he got assigned to in the second 6-month period he went to sales, and then again after that he went to your sales in the next this means, that means 1 year is over, this is the next 6 months. So, therefore, you can see that this diagram, and here for example, here from this onwards he continued for 2 periods consecutively in the production section. So, this you can diagrammatically describe the profile of a employee in the manufacturing company. Now, let us just give some more terminology. So, set of all possible values the random variable xi takes is called the state space. So, we always describe, so wherever the system or the process is, whatever situation it is in, so that will be described by the state space, and normally what we do is we give it numbers. So, the possible values in the state space we describe by the numbers. So, for example, here the 3 sections I numbered as 1, 2, 3. So, it is easier because otherwise you can't go on writing the possible values that the state space contains, right. It may be different things. So, we can just distinguish them by the numbers. And so, here for example, this will be xn is I, means the state in which the system is at time period n. So, the value of xn, so if I am describing my xi's are the variables which are the random variables which describe the process, right. And then when you change these, that means when the system changes from one state to another, we call such process as the change is called a transition. So, are called transitions. Okay. Now, as I said that, and we have seen the 2 examples already, simple ones, we saw that the real life situations, the processes will be many processes are stochastic, because there are elements of the process which are not which cannot be determined with certainty. And then we also have seen that even in such simple examples your xi's are not independent. So, there will be some sort of dependence among the random variables. So, therefore, as I was saying earlier, that it will be very difficult to have a combined joint density function of all the possible random variables which describe the states in which the system can be over a long time period. And so, you cannot just analyze or answer any questions about the process. So, Markov suggested the following simplification. So, he said that the transition from one section to another may depend on the current section occupied, and here I should say the word only. Okay, the transition from one section to another may depend on the current section occupied. So, when we say depend, this is of course that means the computation of the probability with which the section this process will transition from one section to another would be the probability would be dependent on where you are right now. So, the current section. So, Markov suggested this simplification. Now, in the for example, in the watch shop example, value of ni plus 1 to depend on the values of ni and di plus 1 only. and the way I was describing to you the values of n I plus 1, which was max of the formula I wrote down. So, that from there we saw that we were computing n I plus 1 only depending on the values of n I and d I plus 1. So, that was that anyway. So, therefore, according to Markov's definition, this is already satisfying the Markovian property, right. Now, in the okay. So, when once you have this, and then that means in the section assignment problem, what we are saying is that, yeah, that means we are saying that if you want to look at xi, the value of xi, then that will depend on, so the probability that you will go from whatever the value of xi, it will depend on what is the value of xi minus 1. So, sort of the transition from here, so this will depend on this, and then xi will affect the value of xi plus 1 with certain probability, right. So, this is the kind of dependence we are only allowing, or you can say this is a simplification that. So, this makes the analysis of stochastic processes which satisfy Markov's property quite tractable, and we will see this as we go on. We will see that about we can probably answer almost all the questions that I wrote in the beginning about the automobile manufacturing company, and the kind of questions that an employee may be interested in knowing. So, we will be able to answer the questions because if we say that the section assignment process would satisfy the Markov property, right. Now, any stochastic process which satisfies Markov property is called a Markov chain or a Markov process. So, I will be using the word Markov chain or Markov process with the same meaning synonymously, right. So, now what happens that with the Markov's property being satisfied by a process, then we just need to compute the joint or the conditional probability mass function. Remember, I am talking about discrete processes. So, joint or conditional PMF of neighboring xi's is computed. So, it simplifies, and therefore, when you have two variables, you can very easily compute the joint or the conditional PMF of two variables, and so with that we are then able to analyze the process over long term and whatever it is. So, now if you want to formally state Markov's property, that is, see, essentially what you are saying is probability xn plus 1 is equal to j. That means at time n plus 1 your system is occupying state j, and if you look at the past history starting from x0 is I, then it will be x1 is some I1 and so on, xn minus 1 is In minus 1 and xn is I. So, this is the entire past history. So, if you are not assuming the Markov property being satisfied by the process, then of course, to answer this, compute this probability, you would need to know the entire past history. But then Markov's property simplifies it and says that this whole thing can be made equal to probability xn plus 1 equal to j, given that xn is I. So, wherever the the current state of the system, that helps you to determine, so with some probability, where the system will be in the next state, next time period. Okay. And so, these are known as one step transition probabilities. Okay. And we will call them as Pij. So, now I am here not writing anything else. Why? Because I am now making one more simplification, and what we are saying is that this is actually equal to probability of x1 equal to j, given that x naught is I. So, that means the starting state of the system, suppose if you were in, if the system was in I, state I, then the next period that it is in j. So, we will denote that one step transition probability, and we will say that over the long period that the process goes on, this does not change. That means, whether at time period n plus 1 you are considering the change from time period n to time period n plus 1, or you are considering the change from the starting initial state to this first period. So, those probabilities remain the same, and that is why the word stationary. So, what we are saying is that the one step transition probabilities are stationary, And essentially the explanation here is that whatever process you consider, we are saying that after the initial perturbations and so on, the system has settled down to stationary, this system has become, or the process has become stationary. So, it is not and therefore, these transition probabilities are not being affected by where you are considering, at what time period you are considering the transition. Okay. As we go on, we will be looking at lot of processes and lot of situations, real life situations, where we will see that to assume that your transition probabilities have the stationarity property is not very unrealistic. So, we will continue with the so I will just continue with defining and giving you how to compute these probabilities and so on, or once you have these probabilities, then what can you do with these. So, let us start looking at how we will now continue with the analysis of the process, and so therefore, what we would need first to describe the process, and what are the quantities that we will require before we can continue with our analysis and trying to answer the questions related to the process. So, if x naught is the, let us say x naught is the present assignment by our notation, right, 0. So, this means whatever the value of x naught, that tells us the present assignment of the employee, and then we are interested in his next assignment, that is, we want to know the value of x1 in the next time period. So, if suppose x naught is 1, that is, the man is currently in production, then x1 can be 1, 2 or 3, any of the 3 sections he can be assigned to, right. So, that means you want to know the probability. So, it means this has to be given to you, that is, if he is already in, he is starting his career with x naught equal to 1, that means he is in production right now, and then what is the probability that he will be again kept in production only. So, x1 is 1. So, we will call this as a P11, and as I told you that these are one step transitions probabilities, and they are we are assuming a stationarity. So, it does not matter whether it is x n plus 1 equal to 1 given x n is 1, or x naught is 1 given that x naught is 1, then x 1 is 1. So, the probability. So, P11, and then similarly you would need to know if x naught is 1, then what is the probability that he will be in HR. Right. So, that probability is P12, and the probability that he will be in sales is given by P13. Right. So, these are the first step transition probabilities if you know where he is at the beginning of the planning horizon, right. That is, if you know x naught is 1, but if x naught is 2, then of course again the transition probabilities will be different, in the sense that now what is his probability of going from 2 to 1. So, that means he is in HR, and then the probability that he will be assigned to production. So, that must be some probability. You see, these are the transition probabilities which are now describing to us whatever the assignment process is. Okay. And so, therefore, again these 3 transition probabilities P21, P22 and P23 are given to us, and then for if x naught is equal to 3, that means if he is currently in sales, then his probability of going to production will be P31, probability of going to sales will be P32, and probability of remaining in sales will be given by P33. So, these we call as the I am not all the time saying one step transition probabilities, but that is understood. Okay. So, this is transitioning from state. So, here these 3 numbers, these 3 probabilities give you the transition probabilities of transitioning from state 3 to any of the 3 states, right. So, therefore, the process, and now of course, we will see that this is not a complete description of the process, and we will, as we go along, we will find out what more we need, but let us just first look at this. So, now the 9 first step transition probabilities can also be written as a 3 by 3. See, remember, because whatever the number of states, if the number of states is capital N, then your transition probabilities will be n square, because you can go from one state to any of the n states. So, therefore, you will always have n square numbers, and so these transition probabilities can be written in a matrix form. So, if you have n entries n states that this system can occupy, then it will be n cross n matrix that you can record all these transition probabilities in a n by n matrix. So, here since our states 3 states are there, 3 sections. So, I can record all the 9 transition first step transition probabilities in a 3 by 3 matrix. So, P will be called transition matrix. Okay. Now, since the man must transition from, let us say, from production to any one of these sales, either he stays in sale production, or he goes to HR, or he goes to sales, he must transition to one of the, because after every 6 months the assignment is announced. So, therefore, these 3 probabilities will add up to 1, right. Similarly, and therefore, also another way of saying this, that these probabilities must add up to 1, is that they are the P11 and P12, P13 describe the conditional PMF. Remember, we have talked about it while talking about conditional probabilities and conditional expectation. So, this is the conditional PMF of x1 given that x naught is 1. And so, therefore, since these 3 numbers describe the conditional PMF, they must add up to 1, because right. So, same way you can argue that the second and the third rows must also add up to 1. That means, P21 plus P22 plus P23 is equal to 1, and P31 plus P32 plus P33 is 1, right. So, now any square matrix which has, because these are probabilities, so they have to be non-negative numbers. So, any matrix A, a square matrix which has all entries or all elements non-negative, and the rows add up to 1, can be will qualify to be a transition matrix. That means, we can say that there must be a stochastic process which can be associated with such a matrix. So, all entries are non-negative, and the rows, the elements of a row add up to, of every row add up to 1. Okay. So, this will qualify to be a transition matrix, right. Now, another way of looking at this process, because diagrams always help, they fix ideas, and I think they also help in the understanding of the process. So, let us see, I will describe the 3 states by the nodes of this graph. So, first is your production, HR and sales. Okay. And if I am showing it arc from 1 to 2, then this is transitioning from 1 to 2, and of course, I have not entered all the probabilities, but they can be written down here. And so, the arc 2 to 1 will be the transition from one step transition from your HR to production, right. And this loop describes, that means you stay in 1, that means you transition from 1 to 1. So, you do not go anywhere, you continue with the same state. So, this way you can look at this, and so you can write down the probabilities here also, P11, this will be P22, right, and this will be P23, so this will be P32, and so finally this will also be P33, and here this will be P31, and this will be P13. So, this diagram also helps you to look at and you can see that currently you can transition from, for example, from 1 to 2, then you can go from 2 to 3, you can come from 3 again, you can come back to 2, or you can go from 2 to 2. So, actually you can play around and you can see a lot of things that you can do with the, you can see how the transitioning is taking place and so on. But of course, this you can do when your number of states is small, and if the number of states is large, then drawing a picture like this may not be a very good alternative, and so we will have to look at other ways of handling this process. But anyway, this makes the thing look interesting. I mean, the picture is there and you can just see how the process is evolving over time, going from one state to another and going through these arcs. So, you see we described the first step transition probabilities and through the diagram and so on. Now, suppose we want to now look at the x2, the random variable that describes the state of the system at time 2, right. Now, again I try to show you through the diagram. So, if you look at this, for example, you start with state 1, that means you start with production, and after 2 transitions you are back in production. So, what would that mean? So, the possibilities are that you start with production, then you next period you again transition to production only, that means you stay where you are, and then finally you in the next step you again transition to production. So, that means you continue through. So, this path describes one possibility which I have written down here, right. And then it could be that you start from production, you go to HR, and then again you get transition back to production. So, that will be your second path. So, I am talking now in terms of paths, because this is how you will, when you go for 2-step transition probabilities, this is what you will have to compute the probabilities of these paths, and then finally you will start from production, go to sales, and then you are back to production. So, that will be your third path. And so, just to give you and of course, we will continue this discussion in the next lecture also. So, if you look at probability x2, so here your actually, the arrows are in the wrong direction. So, it should be x0 to 1 and then x1 to x2, right. You start from here, then you transition to production, and again you transition to production from the first period to the second period. And since we have the Markovian property tells us that we just need one step transition probabilities, that means the transitioning from x0 1 to 1, and then from in the second period, from in the first period from 1 to this. So, these are independent, and therefore, I can write them as the product of the transition probability 1 to 1 here in the first period, and then again 1 to 1. So, now here again the second property that we have used is the stationarity. So, Markovian property and stationary transition probabilities both tell us that the probability of the first path, that means transitioning from 1 to 1 in 2 periods along the first path, the probability is p11 square. And so, we will continue with this kind of computation and then show you very interesting results, and then you will see that how far our analysis can go of a stochastic process which satisfies Markovian property, and of course, we are talking when the stationarity conditions are met.